Hello everyone, welcome to another ACE Computer Vision Spotlight series. My name is Mahdi Biparva. I'm an R&D engineer at Sunnybrook Research Institute, and I'm hosting computer vision um, talks in this series. This is my pleasure to host another great talk today titled Camera Depth of Field Manipulation for Pre and Post Image Capture. Um, and I'm excited to host our great presenter today, Abdullah Abuolaim, in this amazing session. So Abdullah is a PhD candidate in the Department of Electrical Engineering and Computer Science at York University here in Toronto, Canada. He's uh, also a research intern at Google working with the computational photography team. He received his Bachelor of Science in Computer Engineering from Jordan University of Science and Technology in 2015, and then obtained his Master of Science in Computer Science from the National University of Singapore in 2017. He has been a reviewer for several computer vision conferences like CVPR, ECCV, and ICCV. And his research interests include computer vision, computational photography, and deep learning. Um, so without further ado, let me welcome Abdullah to our session. Abdullah, please take it away.
Okay, hello everyone. First, thank you, Mahdi, for the nice introduction, and thanks for this opportunity to present my work here. So again, I am Abdullah Abuolaim. I'm a fourth year PhD student at York University, Toronto, Canada. I'm working with the Prof. Michael Brown. So mainly our lab, we do stuff related to computational photography. And for my research work in particular, I do the camera depth of field manipulation for pre and post image capture. So I'll start the presentation with the concept in focus and sharp image. So we always, when we capture image, we always want that like the image to be clear and in sharp focus. And to get this clear and sharp image, we need to adjust the camera focus. So to adjust the camera focus, we need to adjust something called camera depth of field. So to know what is this camera depth of field, I'll go with this animation. So as you see here, let's assume we have this simple scenario where we have a camera, we have a person, and we have this green region in real world. So the depth of field is the region that makes the objects appear in sharp focus in real world. So imagine that we capture this person, we capture the image where he is outside this depth of field. So the acquired image will be blurred. So to get this person in focus, what we do, we adjust the camera such that the depth of field is shifted and this person inside, and we can get a sharper, clearer image. So now I'll talk about how we can adjust then this depth of field. So before I talk about how we can control this depth of field, I would just show here this abstract camera where we have a aperture. So this is just a simple model. Real cameras, it's much more complex, but simply the camera is just aperture, then lens, and there's this imaging sensor. So the first way to adjust the camera, the depth of field, is the camera apertures. So in this scenario, again, this green region is our depth of field region, and this is the camera aperture. So going for a narrower aperture, if you capture an image, you see here the background is heavily blurred. But if you go for a narrower aperture, which is smaller one, this will extend the depth of field. Then you see the background is slightly sharper. And if you go for more narrower aperture, then you extend the depth of field and then you can get everything in focus. So mainly the aperture adjustment adjusts or extend the depth of field. Whereas the other factor that control the depth of field is the lens position with respect to the imaging sensor. So you have the imaging sensor, you have the lens here, and then you have the depth of field in the real world here. So let's assume we have also two zebras in the scene in real world. So both are blurred and both are outside the depth of field. So what we can do, we can just move the lens and then we can get the first zebra in focus where we shifted the depth of field. and we move it further to get the other one, and now it's in focus. So mainly the lens position is in charge of shifting the depth of field. There are also other factors that control the depth of field, like the focal length, etc. But mainly in cameras, these are the main things that are used to control the depth of field and adjust focus in cameras. Now, I just asked this question: is it always possible to achieve the desired depth of field? Okay, while cameras' depth of field can be controlled either manually or automatically, the desired depth of field is not always achievable due to, first, we have sometimes physical limitations of the camera optics. So before I capture the image, sometimes some scenarios doesn't allow me to get the desired depth of field. For example, if I want to capture a low light scene, then I need to go with, for example, wider aperture. And as we saw earlier, that will give me a narrow or a smaller depth of field. So that is hard for me to capture like proper exposure image with the current aperture. So there are some physical limitations, and this all before capturing. And also sometimes we capture images and we don't pay attention, but then when we go home and see images like on monitors or stuff, we just realize that the focus is wrong. So we need also, we need something after effect. So my research work aims to address depth of field manipulation from 2 points of views. First, adjusting depth of field at capture time automatically, and this is known to be camera autofocus. So I think most of camera users know about this technology where the camera does the focus for you automatically. And all of this gonna be at capture time. So before capturing the image, you adjust the focus, etc. And the other point is gonna be computationally extend the depth of field as a post-capturing process. As I mentioned, sometimes you just realize you captured the images and the focus was wrong and it's not the focus you wanted. So you need some post-processing. You need to post-process those wrong focused images to be sharper. So first, I'll start with the first thing, which is a pre-capture depth of field manipulation, which is called camera autofocus. So here, just I'll show the current technologies where there are mainly two types: active autofocus technologies and passive ones. So the active ones, the famous thing is called time of flight autofocus, where these systems have a accessory or extra sensor that emit light or send a signal towards seen objects, and then this signal will come back, and then they calculate the round trip time, and then find how far is the distance from the camera, and based on that they can adjust the focus because there's some calibration and they know exactly which lens position can get that scene distance to be in focus. Those systems very accurate because they send the light emit the light signal or a signal to the scene objects and then calculate the distance. But also they are very sensitive to light. So for example, they tend to fail in the outdoor scenes. On the other side, we have the passive systems where they don't use any extra sensors or send signals to the scene objects, but rather they use the imaging sensor only. So the first technology is called phase difference autofocus, and the other one is called contrast detection autofocus. So for the phase difference, it's actually done at the hardware level. So there is no image capture also here. Everything is done at hardware level where the lens or the focus is adjusted before image capture, and then the image is captured. So the good thing about this technology, the phase difference, is that it's very fast. I mean, compared to the other technologies, because all done at hardware level. But the only thing that can do with the phase difference is that you don't have idea what is inside the scene. So if you want to do a high-level computer vision or image processing stuff, you need to capture an image, and this technology just done before capturing the image. So that's why you have to go with the contrast detection autofocus, where you capture an image, and then after capturing the image, you can apply some computer vision algorithms or image processing. For example, for face detection, I want to focus on faces, so I need to capture. I know where's the face in the scene, and then I focus on the face. For the phase difference, it comes with a different designs, sub-mirror, the older one, and on sensor. And then recently, the modern phase difference is called the dual pixel sensor. So also we will focus on this new sensor that mainly nowadays most of the camera using this sensor for autofocus. So for camera video autofocus, nowadays autofocus is widely used in cameras, as I mentioned. The phase difference and contrast detection used to determine the single image sharpness are well established. So mainly with the consumer cameras, let's say smartphone nowadays, the phase difference and contrast detection are the common ones. The time of flight is not really many cameras employ that technology, but rather they employ the phase difference and the contrast detection. So for a single image capture, imagine that you just want to capture a single image. With those technologies, they are well established. They do a great job because, you know, it's easy, just single scene capture and that's it, done. What is more challenging is using those low-level algorithms to determine high-level autofocus objectives, especially when it comes to dynamic scenes content. Like imagine you have a video, and then in this video the camera is moving, the objects in the video are moving also. So it's now challenging. It's more challenging. You have dynamic scenes now. Everything is moving. Everything might be interesting for autofocus. So you need to do some higher level autofocus. So it's different from single image capture. And the just I'm talking about the academia and research, there has been significantly less work on autofocus for video. So it's very hard to find paper, like very few, and most of them, they are old paper and there's nothing state of the art using the current state of the art sensors used for autofocus. And there's one thing worth to mention here. While recording a video, the main thing responsible about autofocus is going to be lens movement, not the aperture, because for videography, people adjusting aperture while recording video will introduce changing in exposure. So as I mentioned, aperture is it allows the amount of light coming into the imaging sensor. So adjusting this in real time, I mean in the recording time, will introduce some exposure change, and this is undesired effect. So what is actually responsible about autofocus for videography people is going to be the lens movement. Also in this research, we've focused on smartphone cameras, and for those cameras the aperture is fixed, so it's only you can adjust focus using the lens movement only. To start the effort, as I mentioned, there was very less work on this video autofocus, and on the other hand, it's very confidential for industry, so we don't know what these, I mean the phones or the cameras, how they implement the video autofocus. So what and even we couldn't find like a white paper or something describing how they work the video in these cameras. So what we did, we kind of like tested in a reverse engineered manner and see how these cameras performs or their behavior, autofocus behavior. So here in this example, I'm showing two cameras, the Apple iPhone 7 and the other one is Samsung S6. So yeah, so one thing to mention here is that these scenes can be repeated exactly the same. So the cameras can see exactly the same thing over time. So we have the same scene dynamics, and then we see their behavior. So if you look here at the time 0, both cameras were focusing on the center region. So both the center region are in focus. But then at the 5th second here, the face appeared in the scene, where the iPhone 7 is just switch or pull the focus from the center to the face region and the face in focus, whereas the Samsung S6 is still focusing on the center region. And for even more time, the face is there, is coming in the scene, but still the focus is on the center for the Samsung, whereas the iPhone stayed focusing on the face region. So this is really interesting and begs the research question, like which region or which behavior is more preferred by users. At the end, we want like users to be happy with the autofocus. So which one users prefer now is the research question. So to address this research question, what we need is that there's one major challenge for developing video autofocus algorithm. The challenge is that in the inability to examine the full solution space. So what I mean here in full solution space, imagine that you have video frames, and for each frame, you don't have access to the different focus layers. So just the frame is captured and you have a single frame at a certain focus layer. So we don't have such data set or something that can provide processing video and uh, processing video with a full solution space. Oh, sorry. Okay, so there are also some additional constraints, like imagine that I wanna my region of interest or my desired lens position is at position 20, and now I'm at position 5. So to go to 20, I have to go over all the lens positions. So I can't just immediately jump from 5 to 20. So this is one thing. And it's a real, I mean, mechanical system that you need to move the lens. So the thing you can do at a certain time point is that to move forward or backward or stay in your position. So this is also some other constraints to address the real autofocus systems. And maybe when you move the lens also, there's time, it takes time. So maybe within the time you're moving the lens from position to another, the scene might change, the camera might move. So this is also another constraint you have to consider when you're developing like a video autofocus algorithm. So then what we need, actually, we need a temporal focal stack data that has a full focal stack for each video frame. So what I mean in focal stack here is that for a single still image, you have captured this image like at different lens positions. Then you have different focus layers. So people call this as a focal stack. So you need the focal stack data for each video frame, which is, we call it here temporal focal stack data. Also, you need a platform that incorporates lens motion, scene dynamics, and frame advancements. So to start the efforts, first we need to prepare this environment that we can introduce some scene dynamics and control the scene motion, and that allow us to repeat scenes for different cameras. So what we did, we prepared this environment where we had 4 linear stage actuators to control scene motion using microcontrollers like Arduino. And then these actuators are synchronized with an Android application that control the camera lens, the smartphone lens, so such that we can move the lens with respect to the scene motion and repeat the scene scenarios, etc. Also, we tested different smartphone cameras. We also use for this setup a DC light. So the actual lights we have here in houses usually is AC alternating. So, but it's a flickering actually. But as a human, our perception is slower than this flickering, so that's we can't recognize this flickering. But when it comes to images, this flickering sometimes is visible. So to have a consistent light between imaging, you have to employ some DC light to avoid the light flickering. So then, after doing this environment, we were able to analyze the performance of 3 representative consumer smartphones, the Apple iPhone 7, Google Pixel, and Samsung phones. So, and then we were able to observe their behavior under different scenarios. As I mentioned the figure before, the difference between 2 smartphone cameras, we also did more experiments to understand how they behave under different conditions and scenarios. So as I mentioned, there's no report or white paper showing how autofocus worked for these smartphones. Then, based on their behavior, we set up like a table of 10 scenes and scenarios where we include like moving camera, stationary camera, different scene motion, if the scene contain phases or not. And there are many things we did to come up with this table based on our observation and analysis of these smartphone cameras. Then we captured our focal stack, 4D temporal focal stack data. So this is again, so here you see you have your output video. So what you see is a single frame. They are stacked to see this, motion over time. But actually our data, which is the first of its kind, there's no such data in the research community. And this is the first that have temporal focal stack. So for each video frame, we provide the full focal stack, which is different focus layers. and so on for each video frame. Here I'll play just a demo how this data browser works. So if you see, you can move in time here horizontally, this slider, and at each time or time point or video frame, you have access to the full focal stack. You have different scenes also. For example, this one has a moving camera. So here we just go through the focal stack for a single image, and then here we have a moving camera, moving scene, and so on.
So just to make it more clear, you basically we can say you recorded the same scene for different number of um, kind of focal length.
True. Yeah. So this is
lens
yeah.
position actually.
Yeah, exactly. So we did this in a stop motion manner. So as I mentioned, we have this camera
I see. Okay.
application where we control the lens, and we have the actuators where we control the motion. So we stop the scene is still. We capture the full focal stack at different lens
I
positions,
see.
and then we move a small step that is not visible. If you see here, the motion is kind of smooth. You don't feel
Right.
it. There's
Right.
any stop motion stuff. So everything, we use the tripod. We made sure everything is still stable to have something look like real videos.
So you synchronize between motion and lens position.
Exactly, in a stop motion manner. So that's why we get. So now we have with capturing this data set, we have like full solution space. So I'm able now at each video frame to investigate the full and change the focus anytime. So here I'm just showing a quick comparison with other data set that use focal stacks. So usually people use focal stack for still images, but for us we have the temporal meaning. So every image is connected with the other. There's some time dependency and temporal dependency. We also introduced images that are the resolution much higher compared to the other focal stack data sets, the spatial resolution. The total number of images we have 33,000, and all real optical images, whereas the other focal stack data set, they use something called litro camera, and this cameras like do some light tracing after effect and apply the defocus after effect. So this is pretty much needed data set. So now we have the data. Everything is nice. We have the full solution space. How we can emulate the real autofocus systems, as I mentioned, the phase difference and contrast detection. So we need an API that mimic those technologies. Also, we introduced, based on our observation, because we analyze different smartphone cameras before we start collect the data or understand how we collect this data, what are the scenes, we also analyze their behavior. So we came up with 5 or 4 different autofocus regions. The first one is the global, which is the whole frame should be as sharp as possible. So find the lens position such that this frame is the sharpest. Or the 9 focus points. I think people, the camera user are familiar with those 2 objectives, the 51 focus points and the 9 focus points. So the 9 one it's if you see the center region is larger, which is center weighted. So this one represents the center based autofocus region. Also, we have the phase detector region. So those actually represent what we have found in the smartphone cameras. Then with this API, we came up with the API, and API calls mimic all the lens motion, the time advancements, etc. And then we were able to generate videos using our API and using our data. And this video looks like real videos. So the one I'll show now is one generated using our API and using our data set. So this is face region objective. So now focusing on the center. Once the face appears, switch the focus to the face. So you don't feel this video is a stop motion or something. It's really look like what we found in mobile phones when we present the same motion dynamics to the smartphone cameras. Then we have the data set, we have our API, we can mimic any autofocus algorithm. So now we are able to answer the question I asked first, like what, which region of interest or which autofocus behavior is more preferred for users, right? Now we have the data, we have everything, we can reproduce videos, introduce different objectives for the same scene, and then see which one the user preferred. So here I'm showing some results where you have the the x-axis is the total number of lens positions for the whole scenario and whole video. And here's the user preference normalized from 0 to 1. And then those shapes are represent different autofocus objectives. So what we found that there is a high correlation or negative correlation between the lens position movements and user preference. So if you look here, there's minus 87 negative correlation with the lens movements. Also here, minus 99.99 correlation with the lens movements. There's one exception here, wasn't really correlated, which is the face region. So once the face, if the face is close to the camera, in this category, there is a face and close to the camera. So if the face is close to the camera, users still prefer face to be in focus, even though it has, introduced more lens motion to get the face in focus, but still users prefer the face to be in focus. So the main takeaway message here is that lens movements, or users in general, they don't like too much lens movements, which is kind of intuitive. Like when you take a autofocus video and see this video or focus wobble, so this is undesired effect. So nobody likes this effect. So, but before this study and before this data and API, there was no study or concrete thing that tell this fact. But now with this study, we know there's a high correlation between lens movements and user preference. Based on that, so for a certain autofocus objective, we found that conventional wisdom would suggest, okay, you're doing autofocus, so your target is just get the video frame as sharp as possible. However, this is the conventional autofocus will introduce for you, like it's autofocus, make it as sharp as possible. But unlike single image capture, the lens movement is visible in the captured video. So you are not just capturing one image and that's it. If you have a video, have time, then if you move the lens too much, this will be visible. So your target should not be only sharpness, but also lens movement. So there are two parameters to optimize for video autofocus. Sharpness, I want my region of interest to be as sharp as possible, but at the same time, I want less lens movements if possible. So how to do that? Our data set and our API and some insights from the user study that there's correlation with the lens movement led us to come up with two smoothing methods. So what is the idea here? What I'm showing here is that I have time, so over time, and this is the lens position over time. So imagine we have some certain video sequence, and the black one is the conventional autofocus method that try always to get the maximum sharpness for this region of interest. So if you look at the sharpness over time, and then we have the red one is the smooth autofocus. So just by applying some offline smoothing method, we were able to get almost as the same sharpness as the conventional one, but the lens movements are much lower. So this is our goal now. Our goal is to come up with algorithm that guarantee for you sharpness for the region of interest, but at the same time optimize the lens movements. So the first method was supervised bidirectional, LSTM. So the idea of this LSTM, it's an online method. So just given my current lens position, try to predict my next lens position, if it is gonna be forward, backward, or stay in my position. So it can be shown as a classification problem where you output either forward, backward, or stay in your position. So we use some offline methods to get the training data for this method because it works online. So for offline, what I mean offline methods, they see frames in the future. So they know some future data and then optimize the current lens position based on future and prior lens positions. But in real scenarios, we don't have this. We only can implement we can perform in an online manner because we don't see future. So this method is online and trained using some offline smoothing methods. The other one was unsupervised. So we found another simple but very effective method. It's completely unsupervised. There's no training, there's nothing. It's just a simple weighted moving average. And the idea here behind is mainly that the lens position will be weighted by the distance from the optimal lens position. So if I'm that means, in other words, if I am far away from my optimal region of interest, so that means it's really worth to go there. But if I am somewhere close around the optimal, it's okay to be around. No need to introduce more movements because the sharpness will not be that much. So it is simply weighted moving average. So with these two methods, we were able to significantly reduce lens motion up to 64%. So if you see here, we have the online methods, the supervised one, the bidirectional LSTM, and the weighted moving average. And if you see how much reduction of lens movement, we were able to reduce much the lens movement. Also, with this reduction, there was a small loss in sharpness, less than 5%. If you see here, all the sharpness change is very small compared to the lens motion reduction. And this is achieve our goal. Also, one more thing is these things, I mean, less lens motion is not only preferred by users, but also if you talk about power consumption, because for power consumption, if you want to move the lens, you need power, you need energy. So with lensless movements, then you will reduce the power consumption in these devices. After smoothing the videos, we did another user study, and the idea to see that which one preferred. Is the method the conventional autofocus that always target the image sharpness preferred over our smooth one that consider lens motion? So what we found, our two smoothing methods, they were preferred over the conventional one. And even the supervised, the simple one was the highest preferred one, which is really nice because this very simple and can be easily incorporated to real devices with very small computational complexity or computational power. And this thing here in yellow is just we made a video that is all out of focus. And this video was made just for a sanity check, because at that user study, we were offering some candies. So we put this video to catch people who were not serious and they're doing the studies for the candies. So I'll show here one video before smoothing using just conventional autofocus method. So this one before smoothing. Look how the lens wobble, you see, is not stable. And this effect is undesired because the camera trying to access to get the face, but it couldn't. So, and this is the video after smoothing. So this lens wobble, we get the face and the face is out and we back to the center region. So we see like a clear improvement in terms of lens wobble with these two methods. So the contribution, as I said, dataset with the API, we were able to have this environment to do scenes in a repeatable manner. We analyzed different autofocus behaviors. We conducted different user studies. We also introduced two online lens motion smoothing methods. And those contributions were published in two different papers, one of them in ACCV 2018, as shown here, and one in the WACV 2020. So all of that is about autofocus and is about before image capturing. So imagine that you captured an image and it's already you realize you need something to fix the focus. The focus is wrong, so you need some defocus deblurring after effect method. So I think I'm almost running out of time. So yeah, I'll maybe take 5 more minutes just to introduce these things really fast, and then we can go for more questions. So yeah, this is just a use case that show you the the capturing images with wider aperture sometimes is required for, to go for a higher shutter speed, to go for a higher exposure. So, but then this will introduce defocus blur as shown here. So one way, either you do motion deblurring, but using some state-of-the-art motion deblurring, those cases are hard. But on the other hand, we can do some defocus deblurring here. So the idea, in general, the defocus deblurring After Effects is a very hard problem due to many reasons, due to the spatially varying defocus blur, etc., and based on the depth in the real world scene. And there was lack for real data sets, only light field data using litho camera, which is somehow synthetic defocus blur data. So we use the dual pixel sensors, and mainly the idea of dual pixel sensor that at each pixel location we have two photodiodes. They capture the light rays coming from two halves of the main lens as shown here. And then these two halves, if you subsample those pixels, you can get two different views. And the nice thing about these views, they are correlated with the amount of defocus blur. So if you compare them, the things in focus is kind of like there's no change or no difference, whereas the things that are out of focus will be shifted in different directions. So here's some study showing that the regions that captured between the two views, the left and right dual pixel views, they are highly correlated because they are in focus, but for the out of focus regions, there's lower correlation. So here I'm showing the motion where the focus is, correlated with the amount. I mean, the defocus correlates with the amount of motion here. So the tree is in focus and is not moving, whereas the background is moving because of the defocus blur. So that's why we capture the data set that we were able to, with some camera parameter, to capture a sharp image with respect with, an image with defocus blur with its corresponding sharp image. And for this image with defocus blur, we have the dual pixel views. And then we use those views because we know that there's correlation between the shift between these views and the defocus amount. So we use these views to deblur the images using like symmetric auto encoder with the skip connections, CNN-based model. We get numbers like state-of-the-art.
So, sorry to jump in. What do you predict at the end of the network? So what is I star S?
Is the single sharp image. So your input will be the left and right views of the blurred one, and your target is this sharp image.
But where do you have the sharp image from?
The ground truth. So we came up with a capturing procedure here.
Oh, I see.
So I skipped the details. So the idea is
gotcha.
is you adjust the aperture. So here we capture at wide aperture.
You
and
kind of take the picture for the ground truth.
Yes, it's a picture. Yeah, with some settings here. Yeah, and then we predict this. We were able to achieve the state-of-the-art numbers. Here I'm showing some qualitative result of deblurring. So this is the input, the deblurred one, and the ground truth. Can you see the animation? If it's fast.
Yeah, it is.
Okay. This is another results from the Canon camera.
So there is no depth information into the model. So it's just the left and right, and the model aims to predict. Okay.
Yes, it's end-to-end, like from the dual pixel views that have defocus blur to the sharp image. Also, we tested this model because our capturing requires a DSLR camera that has adjustable aperture, and not all. Even though most of the cameras use the dual pixel sensor, but not all of them give you access to the dual pixel views. Only one DSLR camera, what we know is the Canon Mark IV 5D Mark IV camera. So this is the only DSLR allows access to the dual pixel views, and you can adjust the aperture with these cameras. Whereas in the smartphone, the aperture is fixed, so we couldn't capture ground truth for smartphone data. But what we can do, we just test some data from smartphone. So we tested some
dual pixel sensors in.
Yeah, this is the only smartphone to provide access to the dual pixel views, even though most of nowadays smartphone cameras have dual pixel sensors, but accessing them is not easy. So this is results also from the pixel phone.
Mhm.
Also, deep blurring is important. For example, this image with the defocus blur, the segmentation is not as accurate as you deblur this image. Also, for this scene, the deblurring can improve the depth estimation. So deblurring the image before processing it for image segmentation or depth estimation is good for computer vision tasks.
Mhm.
So this was published in the recent ECCV 2020. I'll stop at this point, so because I think I went over time. I took me longer than
No, it was
I
great.
expected.
Actually, I was enjoying your presentation.
Thank
So
you, man.
thanks a lot. Actually, I really enjoyed that. It's always fascinating to go over the advanced, cutting edge technologies and that sort of thing, with real applications. So I have a number of questions. So are the two datasets you just described, are they available? Um,
Yes.
so
So
so you
yeah, I
have
can
your
provide.
website and people can find it on your,
Yeah,
I
exactly. If
guess.
you search my name, everything is available with the codes, etc.
Okay, that's amazing. And let's see. So did you face any difficulties in the training of the network? So any particular trick that you needed to make? How many data samples did you have for the training?
So for we train batch wise, and this is the only thing we were debating how would all these parameters, how much is the batch size, what is the best model. So the symmetric autoencoder, with the skip connections, it's like unit alike, they call it architecture, have been demonstrate really good performance for deblurring in general, like motion deblurring, etc. So that was our first thing we tried, and it was working. But then the other parameters like batch size, the depth of the autoencoder, how deep is the model, all these things with experiments. So there was like the actual deep learning babysitting stuff
Yeah,
mainly.
yeah. So did you use what was the input size to the network? Did
It's
you resize down sample the images? Because I assume the images are quite
Yeah,
large.
yeah. So we had a data set of 500 pair of images, the sharp and the blurred one, and those are full size frame. It's 4,000 by 6,000, and they're pretty large. So we downsample two times,
I see.
uh, and then we extract batches after downsampling those. So we extract batch
Oh,
of
I see.
size 512.
Oh, so you got into the kind of patching regime that you kind of take patches from the original image and then feed it into network.
Yes, true.
I see. Okay, interesting. And so I assume you didn't try any semantic level modeling of this problem. So currently there is no semantic in your network whatsoever, right? So it's
Yes,
just low level sensor information into the network.
yes.
Okay. And the input wasn't R kind of 255 RGB, so it's not 8-bit RGB, it's just
Yeah, this
real
is a
RGB.
good point. It's there's something about the Canon camera. We tried the raw images, and there was like a slight, uh, intensity difference between the views if you extract them from the raw image immediately. So
Mhm.
we didn't know how we compensate for this right difference in intensity. Whereas the Canon provides a tool that processes the image from raw to
Yeah.
sRGB space, but
Mhm.
at the same time, you can get views with, they have a nice, there's no balance intensity, etc. They are, there's no any difference,
Mhm.
nice views, and also provide you with a 16-bit depth images. So it's kind of like, still 16-bit depth images, which is equivalent to RAW somehow, but it's actually processed to the sRGB space. So
I
it's
see.
not raw images.
Mhm.
Because of
Cool.
this intensity difference, we decided to use their tool and extract those 16-bit high
I
quality
see.
images. There's one point also when we capture the data set, it's low ISO data set. So we tried to, adjust the exposure and shutter speed with a low ISO, because low ISO will give you a clean data, less noisy data. So the data, that's why we call it high quality with a 16-bit depth. So it's a pretty
I
useful.
see. Right. Yeah, I'm pretty sure. And the other thing is, I have a question with respect to the first part of your presentation. So you mentioned you tried one unsupervised approach and one supervised, the part
Yes.
about the controlling the movement and sharpness. So one question I have is, so with respect to the unsupervised one, you kind of mentioned that intuition is just to avoid getting to the optimal point. So it's kind of a slows down as it gets closer to the optimal and kind of gets eager as it's far away.
Yes.
So does it mean that it's kind of try to avoid to the gets to try it tries to avoid getting to the optimal point? So it's just like slowing down. So it never gets to the optimal.
We if you remember the equations there, I really go fast to the equations. Yeah, we have this beta parameter here. So if you see this beta,
Right,
yeah, beta controls this thing you mentioned. So yeah, we adjusted the beta
right.
such that, so you can just view it as that if your optimal lens position stay for a long time, let's assume your optimal is there for like 10 frames, then this equation should take you there.
I
If
see.
your optimal just appears for one frame, then
I see.
no point to go there, right? It's far away. So what's the point if I go there and then my optimal changes, right? So this is
I
simple
see.
method, and we can control this how fast or eager, as you mentioned, with this parameter beta here.
I
So it's
see.
exponential. So
So it's kind of the time that kind of implies how much fast it
yes,
has to move toward the optimal point.
yes,
I
and
see.
also
Okay.
it's equation of time. So if you're optimal
Mhm.
there for a long time, then you have to move
I
there
see.
because your optimal is there for a long time. So it's worth to go there.
Okay.
Yeah.
Very nice. Yeah. Thank you. So actually, I'm almost to the end of my questions. So I would like to thank you, Abdullah, for the great presentation. It was
Thank you.
very interesting. Thanks for your time. And I would also like to thank the audience for joining us and hope to see you all in the next talk. So thank you. Have a good night, everyone. Thank you, Abdullah.
Thank you. Have a good night. Take care.
Thank you.
Bye bye.